Hello everybody, welcome back to Computational Nanophotonics videos. I'm Josh, and today I'm going to walk you through how to write your own 1D FDTD code with Python. So first of all, if you don't know what FDTD is, welcome to my channel. You obviously haven't seen my other videos, so please check that out. But FDTD is the Finite Difference Time Domain method, and it's a brute force method for solving Maxwell's equations in the time domain. The other option being in the frequency domain, because time and frequency are duals of each other. FDTD is probably, I'm going to say most likely, the most commonly used method for solving Maxwell's equations in photonics and nanophotonics. And the reason for that is, first of all, it's kind of physically accurate, right? You're solving Maxwell's equations in time instead of frequency, so you get to see what's actually physically happening. And it's also kind of the easiest method. There are other methods. There's finite element methods. There's the discontinuous Galerkin time domain method, which has been picking up a lot in recent years. But FDTD is kind of the most simplest, and it's quite accurate for solving Maxwell's equations. And also, you can get some really cool videos out of it. So I'm going to show an example of that from a colleague of mine who's now a professor out in Germany. Antonio Calalacina. Check out his papers on Google Scholars if you want. But here's a video of a FDTD simulation. So you have a plane wave coming in, and it hits a silver surface covered in silver nanoparticles, spherical silver nanoparticles. So this is just a cross-section of a three-dimensional simulation. So here you can see how the electric fields interact with the silver particles, and you can see these localized surface plasmon resonances in the silver particles. And from this simulation, you can actually acquire a lot of data. So you can actually calculate the reflection spectrum. So if you place like a flux monitor up here, you can calculate how much light was reflected from this surface, and you can get a reflection spectrum out of this. And actually for this specific project, what it was found is that these nanoparticles actually change the color of the silver that they're sitting on. So silver, as you know, is very highly reflective in the visible. So if you have a silver sample and you shine light at it, the light will be mostly reflected back. Now, if you put these nanoparticles on top, you can actually change the color of the silver. And what I mean is, like, you shine light at it and you'll see that, oh, it's green now, or it's blue, or it's purple. So that's the beauty of plasmonics. Maybe one day I'll go deeper into that. But FDTD is driven by solving Maxwell's curl equations, because the Maxwell's curl equations are the two equations that kind of describe the dynamics of the electromagnetic field, right? Because they have the time derivatives. Okay, so to solve these equations, we're going to use finite differences. So let's talk about that for a second. This is a definition of a derivative. If you haven't seen this formula before, maybe you should go back and review some calculus, because calculus is very important in the study of electromagnetic theory, and you should probably know it before you try to solve Maxwell's equations numerically. But anyway, this is the definition of a derivative. So you have some function f at x, and you want to know its derivative at that point x. So what you do is you evaluate that function at x plus some value h over 2, subtract f at x minus h over 2, divide that by h, and take the limit as h goes to 0. So for a smooth continuous function, that will converge to the derivative. So what a finite difference is we actually take this h, and instead of saying, let's put the limit of h to 0, we just set h to be a very small number. We can now approximate this derivative using this formula here. So I replaced h with a delta x, but for sufficiently small delta x, this formula here is an approximation of the derivative. So let's plot that out here. So here's a graph of what I believe to be a sine function here, and we want to know the derivative of this function with respect to x. So according to this formula, we just need to take 2 points, one that is delta x in the left y direction and one that is delta x in the y direction, and we evaluate the function of those 2 points. And then we just do this calculation here using those. An important concept here is that this derivative is centered at the point x, right? Because we're evaluating it using a point x plus delta x over 2 and x minus delta x over 2. So the middle of those 2 points is x. So when I say that this derivative is centered at x, that's what I mean, is that we're taking 2 points on either side of x. There's another formula for numerical approximation of a derivative, and that's this formula here. Now you'll notice here that I didn't say that this is at x because it's actually technically not at x. This derivative is centered at x plus delta x over 2. And the way you can see that is, again, plotting it out. Here, we have this formula, so we take a point f at x plus delta x and f at x, and in the middle of those two, we have the point f at x plus delta x over 2. So this formula here calculates the derivative not at x, but at x plus delta x over 2. So this derivative is centered at x plus delta x over 2. That's an important concept when you're solving derivatives numerically. And it's a very important concept in FDTD, as you shall see. So now we know how to do a finite difference approximation of a derivative. So let's do it now for this term that's circled in red here, this derivative of the magnetic field with respect to time. So here you can see that I approximate the derivative by taking h at t plus delta t over 2. So we take some small step in time, divide that by 2, and we take a step in time backwards. We do this difference, divide by delta t, and that's an approximation of dh by dt. And this is equal to the curl of E at t. Why the curl of E at t? It's because this derivative is centered at t. Remember before, you take a point on one side of t, and on the other side of t, that derivative is now centered at t. Okay, so this tells us that we need to know h at these half time steps, right? If we want to evaluate this derivative here, we need to know h at t plus delta t. So we need to know h at the half time steps. And to evaluate the curl of E at t, we need to know E at whole time steps. So now let's look at this derivative with respect to E. So again, we need to know E at whole time steps. So we're going to have, now we're going to take our derivative. So this is actually wrong. I made a mistake here. So let's fix this quickly. It should be at t plus delta t divided by 2. There we go. Our derivative of E at t plus delta t over 2, because it's centered now at the half time step, is equal to E at t plus delta t minus E of t, and that's going to be equal to your curl of h at t plus delta t, because this derivative is centered at t plus delta t. So this is actually quite self-consistent. So we can actually kind of plot out the time derivative algorithm here. So we have our initial conditions, h at negative delta t over 2 and h and E at 0. So we assume we know these values. Just a small hint here. These are typically just 0. We usually, in any sort of FDTD code, we set these values to just be 0 initially. But knowing E at 0 and knowing h at negative delta t over 2, we can calculate h at delta t over 2 using this formula here. And then knowing that, we can now calculate E at delta t, calculate h at delta t plus delta t over 2, and et cetera, et cetera, et cetera. So we calculate E at these full time steps, and we calculate h at these half time steps. So this is kind of a leapfrog algorithm. So if any of you guys have ever done molecular dynamics before, you've probably seen the velocity, I believe it's called the velocity-Viret algorithm. It's been a while since I've done molecular dynamics, but that's also another leapfrog algorithm. So FDTD is considered to be a leapfrog algorithm because you calculate h at a half time step, then E at a whole time step, then h at the next half time step, and E at the next full time step. Again, I'm just trying to drive this into your brain, so I'm sorry if this is repetitive. All right, now we got to do the curl equations, and these are, you know, anyone who knows a bit of calculus, or I mean, if you're here, hopefully you know calculus, but you know that curls are gross and ugly. So what do we do with those? Well, sorry, Will Smith. By expanding these curls doesn't make it look any nicer. This is why I'm going to go into 1D, because jumping straight into 3D FDTD is quite difficult. So we're going to use the 1D approximation. So we're going to assume that propagation only happens in the y directions. So that means that any sort of x derivative or any sort of z derivative is equal to 0. And we're going to assume that our field is x polarized. So the only component of the electric field is the EX component. So EY and EZ go to 0. Now, our curl, much to Will Smith's happiness, is now just this one term here. And that should hint at you that the only component of the magnetic field is now HZ. So now these are Maxwell's curl equations in 1D. So now we only need to solve this derivative here numerically, and of course this derivative here, but we'll get to that. So we take our numerical approximation of dEx by dy, and so we say we're going to use the derivative centered at the half step, so at y plus delta y over 2, so you can see that over here. So our derivative is EX at y plus delta y minus EX at y divided by delta y. And again, this derivative is centered at y plus delta y over 2. Again, just trying to hammer this in, because this whole grid and half grid thing is actually very important in FDTD. So this formula here tells us that we need to know HZ at these half space steps, and we need to know EX at the whole space steps. Similarly, we can now do the derivative of HZ with respect to y, and you can see here that HZ is evaluated at the half space steps, and EX here is evaluated at the whole space step. So this is the whole idea behind Stagger grid, also known as the Y grid. So HZ is defined at the half time step and at the half space step, and EX is defined at the whole time step and at the whole space step. Of course, you can rederive this for, like, you can say that EX is defined at the half time step and the whole space step, but then H will have to be defined at the whole time step and the half space step. But for now, just stick with my layout here, because it's easier just to copy what I'm doing than to rederive it yourself. But if you are a keener, feel free to rederive it yourself and see what other combinations of whole and half steps you can get. Okay, so now we're going to discretize space and time. So this is a common theme in any sort of finite difference solution, is time and space are not going to be continuous in the simulation. Everything is pixelated, because computers, with the exception of symbolic programs like Mathematica, computers can't do continuous functions, cannot do continuous space and time solutions. Everything has to be pixelated. So we break up our time, t, into these chunks. So these chunks have a size of n times delta t, where n is equal to an integer, and we break up space similarly into chunks, j times delta y, where j is equal to some integer. So you can kind of plot time and space on this grid, where we have j is equal to 0, j is equal to 1, all the way up to j max on this end, and of course time is equal to 0, time is equal to 1, all the way up to n max. So with this in mind, we can now take our entire finite difference version of the electric field curl equation. So in case you're wondering where that came from, that's this formula here, where I put in the finite differences for the spatial derivative and for the time derivative. So that's all. I'm going the wrong direction. Sorry, guys. Okay, so this is all of that right there. And we're now going to put this into index form. So we're going to replace our y's and delta y's and t and delta t with the indices j and m. So y plus delta y over 2 is just j plus 1/2. T plus delta t over 2 is equal to n plus 1/2. And similarly, y plus delta y is just j plus 1, and t is just n. So this is kind of index formulation. Similarly, we can do that with the electric field curl equation as well. So now you can see on this grid that we had before, we can actually see the staggered grid, right? So on this grid, the x's represent where the electric field is solved in space and time. So it's solved at the whole space steps and the whole time steps. and the magnetic field are solved at the half space step and half time step, so they're kind of in the middle of each grid point. And for simplicity, I color-coded the electric field and the magnetic fields here for you. Okay, so the reason why we like this staggered grid is that it maintains the central differences. If you're interested in what that means, what central differences are, I would recommend picking up any sort of numerical methods textbook, because there are central differences and then there are forward differences and backward differences. Central differences is what the FDTD algorithm is based on. It's what we've been using this entire time, and it's the most accurate of the finite differences. It is second order accurate, whereas the forward difference and the backward differences, they are first order accurate, which means that they are less accurate. Of course, there are higher order finite difference schemes that people have used for FDTD, but the central differencing scheme is the most common one, and it is accurate enough. Now we're going to derive the update equations. And from now on, so I put this note here, from now on, I'm going to ignore this j plus 1/2. I'm just going to say j instead of j plus 1/2 in the magnetic field terms. And similarly with n plus 1/2, I'm just going to make it n. So that simplifies the notation, and it's also for computer implementation, because when we go into the code and we make indices, you cannot define a half index. So in the computer code, we're going to have the magnetic field at j and n. But what we know in the back of our minds is that that's actually at j plus 1/2 and n plus 1/2. But again, we can't put that into the code, at least not with Python. All right, so if we take our formula, so this is this formula here. Oopsies, there we go. Take that formula without the halves, of course, and we rearrange it. We can now solve for hz at jn. And all you need to know is hz at jn minus 1. So that's the previous time step. It's the previous step in time. So we already know this. This was solved at the last time step. Plus this term here, where we need to know ex at n and, well, ex at n at j plus 1 and ex at n at j. So this was also solved at the previous time step, though that might not be obvious to you just yet. And here, so here are both update equations for both of those curl equations. So here we have the ex update, where ex is updated to n plus 1 using the previous time step value of ex, and of course the values of h that were calculated in this formula here. So at each time step, we're going to update hz at jn for all j, and then we're going to update ex at j n plus 1 for all j. So when we have this formula, we know already what ex at n is, and when we go to this formula, we know already what hz at n is. Finally, we now have this algorithm. The FDTD algorithm in its most simplest form is this. You have a for loop over your time steps n, from n is equal to 0 to whatever maximum time step you want. And the first thing you do is you update your magnetic field. So you have this loop for j is equal to 0 to j max minus 1. The minus 1 is important. We'll get to that in a second. You update hz at jn is equal to hz at jn minus 1. So that's the previous time step plus this formula here. And we already know what ex at n is from the previous time step. Next, we then update the electric field. So we go for j is equal to 1, again I'll get to why it's 1, to j max, and ex is equal to j at n plus 1, and we just need to know the ex from the previous time step, and we need to know the h's that we just calculated here. And that's the basic FDTD algorithm. Okay, so why j max minus 1? Well, this is just because of this term right here, this ex at j plus 1. So if your array if your Python array is of size j max, well then if you try to evaluate at j max plus 1, you're going to get an error. You're going to get a memory error because you didn't allocate that memory. So we need to actually cut it off somewhere. So we're going to cut it off at j max minus 1 for this loop. Similarly, for the electric field update, you need to know j minus 1, right? So if we started at j is equal to 0, then we need to know the -1th index for the magnetic field. And of course, that's not in memory either. So we need to cut that off. And now that brings us to boundary conditions. So how do we calculate hz at j max and ex at 0? So we'll get to that in a second. But before we get to that, we need to talk about something rather important here. Oops. We need to talk about the step size and stability. So for accuracy, to avoid any sort of numerical dispersion, we need to pick a step size that is less than or equal to the minimum wavelength that we're interested in divided by 20. So you might be wondering what I mean by numerical dispersion. And just because of the discrete grid that we're solving Maxwell's equations on, there's actually an artificial dispersion that occurs. And to reduce that, you need to pick your step size accordingly. So lambda by 20 is kind of the rule of thumb used in FDTD. And because FDTD is broadband, so you can have a lot of wavelengths all at the same time in your simulation, you need to pick the minimum wavelength that you're interested in and define delta x to be less than or equal to that divided by 20. And for stability, we need to pick our delta t to be less than or equal to delta x divided by c, or c being the speed of light. So what I mean by stability is that if delta t is greater than delta x over c, even if it's like, 101% of delta x over c, you'll see that your electric fields go off to infinity because it's unstable. So if you're interested in these sorts of details, then I recommend going into an actual serious FDTD theory book where they will actually derive all this stuff for you mathematically. Another thing to keep in mind is what you're simulating. So we're doing 1D FDTD, so the only kind of structure we can have are thin films and substrates. So let's say we want to simulate light hitting a thin film, and the thickness of that thin film is D is equal to D, all right? We need to pick delta x to be much smaller than D for accuracy, right? So if we pick delta x equal to D, then our thin film is only one FDTD cell across, which means that the electric field inside is only going to have one value. And of course, for a sufficiently large thin film, the electric field could actually vary over several wavelengths inside of this thin film. So we need a step size that represents that. So we need a step size to be much less than the thickness of our thin film. So kind of a better rule of thumb for your step size is the minimum between lambda by 20 or d over 20. So this is kind of like, again, it's a rule of thumb. I recommend doing some convergence testing if you're actually planning on using these results for something serious like a paper or a thesis. Make sure you do some convergence testing, but this is a good starting point. Finally, for stability, we're just going to use delta t is equal to delta x over c. So that's unconditionally stable. So we shouldn't expect any sort of instabilities there. For the boundary conditions that I mentioned earlier, we're going to use what are called MER, absorbing boundary conditions. So this is E at x at j equal to 0 at time step n plus 1 is going to be equal to E at x at j equal to 1 at the previous time step. Okay? And finally, we have our magnetic field at j max at time step n is going to be equal to our magnetic field at j max minus 1, again at the previous time step. So these formulas are quite nice, quite simple to implement, but they only work if delta t is equal to delta x over c. If you pick, let's say, delta t equal to 0.5 times delta x over c, again, it has to be less than or equal to, then these formulas actually change something a bit more complicated, but I'm not going to get into that right now. There's plenty of resources online and books that'll introduce you to the MER boundary condition. If you don't have this boundary condition, what happens is that you're basically saying, well, the electric field at j equal to 0, for example, is going to be 0. Like you're never updating this point, right? So when your electric field is 0 somewhere, that means that you actually have a perfectly electrical conductor at that point. Because the electric field, if it's 0, it's either you didn't introduce a field, or if you did, then you're in a PEC, you're in a perfectly electrical conductor, which means that when the electric field hits the point j equals to 0, it's going to be reflected back into your simulation domain, right? So let's say you have a wave, it comes and hits your thin film, and that wave is supposed to kind of, transmit and also reflect, and then those go hit the sides of your boundaries, and then they'll get reflected back into your simulation domain. And you don't want that. You want them to go off to infinity. So that's what these boundary conditions do. It just makes sure that your electric field goes off to infinity. And I will show you that when we write the actual code. And the final thing that we need is a source, right? If we just use this algorithm with the boundary conditions and the right step sizes and all that stuff, well, everything is set to 0 at the beginning. Nothing will get updated, right? You can run this loop a billion times, but your fields will stay at 0. So we need a source. So we're going to pick a point in our simulation domain, and we're going to introduce a source. So we're going to use a modulated Gaussian. So that's what you see here. We have a Gaussian function multiplied by this sinusoid. So what that ends up looking like is what you see down here. So you have a Gaussian envelope, right? So it goes up and then it goes down. So that's your Gaussian. And then these sine waves here, that's your modulation. And you have to pick omega naught to be some frequencies. Let's say, I would say if you're interested in a bandwidth of frequencies, then pick the middle of that bandwidth to be omega naught. We're also going to introduce a magnetic field source. If we don't do that, if we just introduce the electric field source, then at that point where we're introducing the electric field source, we'll see that the waves propagate in both directions, in the positive and negative directions. If we introduce a magnetic field source at a slightly different point and at a slightly different time, we actually can get unidirectional propagation, and I'll show you that as well. So our final algorithm, this is the full 1D FDTD algorithm, looks something like this. We have our loop over our time steps from 0 to n max. The first thing we do is at a given time step is we update the magnetic field boundary condition, right? So hz at j max is equal to hz at j max minus 1 at the previous time step. We then update the rest of the h fields, again using the previous time step. And then we add in our source. So we're going to pick a point, j source, and for the magnetic field, we introduce the source at j source minus 1, okay? And plus h naught at t, where h naught is our source. Then the next step is to update the electric field. Again, we start with the boundary condition, j at j equal to 0 is equal to ex at j equal to 1 from the previous time step. We then introduce the rest, we then update the rest of the electric field points, and then we add in the electric field source. Here, we introduce the source at j source, and we introduce it for a time at t plus 1. Or sorry, this should be actually, I'm going to correct this quickly, guys. This should be at n. Again, because we're using the index notation, so n plus 1. Okay. Well, I mean, if you looked at the PowerPoint, you can see the cat's out of the bag. This is the end of the PowerPoint. We can now start coding. Actually, before we start coding, I realized here that I made a little mistake that will screw us up if we write the code exactly like this. So I'm going to correct it right now for you guys. This should be a minus h naught. One thing I also didn't mention is with the magnetic field source, it's the exact same as the electric field source, but we're dividing by the impedance here. So that's the square root of mu naught divided by epsilon. So in vacuum, let's say if we're introducing our source in vacuum, this would just be mu naught divided by epsilon naught. But we'll see that in the actual code itself. All right, so I'm going to put this back to full screen again, and I'm going to switch over to my Spider IDE. So this is the Spider IDE. I had something running there before, so I'm just going to restart the console. If you are new to Python, then I recommend you watch a tutorial on Python, NumPy, Matplotlib, and all that stuff before you watch the rest of this video. And also, if you don't know how to download Python, I recommend using the Anaconda Python package manager. because not only does it give you the spider IDE, this nice program here, it also gives you all the modules that you need for any sort of numerical or data science project. All right, with that in mind, we're going to load the NumPy and matplotlib modules to start. So import NumPy as NP, and we're going to import matplotlib.pyplot as PLT. So those are just your numerical Python and your plotting libraries. The next what we're going to do is we're going to introduce some of our constants. So we need to define our permittivity and permeability of free space. So that's epsilon 0 and mu naught. We're going to define our speed of light in vacuum. So that's, we call it C naught. And that's going to be equal to NP. What is that? Oh yeah, 1 divided by NP dot square root of epsilon 0 times mu 0. And let's just, oh yeah, I got to save this. So let's call this 1D FDTD example. There we go. All right, so I'm just going to run, I'm going to run this quickly. There we go. And make sure that my speed of light is correct. Right, it is about 3 times 10 to the power of 8. Perfect. And also, we also need the impedance of free space, which is just NP dot square root mu 0 divided by epsilon 0. And that's about 377, right? Well, yeah, 376.7. Yeah, perfect. Okay, so now we need to define the size of our simulation domain in space. So we're going to define Jmax, the same notation I used in the PowerPoint, and we're going to say it has 500 cells, which is just an arbitrary case. We also need to define the max time step, so we're going to say nmax, and we're going to say that that's equal to, let's say, 2,000 for now. We now need to define our electric and magnetic fields. So we're going to just start those off as zeros. So I mentioned earlier the initial conditions in most FDTD programs is just zeros. And luckily NumPy has a function for that. So we're going to define our electric field as NumPy.zeros of size Jmax. So there's an electric field point for every Jmax point, for every point in the y direction. We're also going to make our magnetic field the exact same size, so HZ. Also, just for simplicity, there's a way to go around this, and maybe we'll do that in a bit, but we're going to define the previous time steps fields as well, which is just more for your sake than for mine. If you've never done this before, this might just make what's happening a lot clearer. And what else do we need? We also need to define a step size. Let's define a minimum wavelength, actually, instead of a step size. So we're going to say that minimum wavelength I'm interested in, let's make it the bottom of the visible. So let's say 350 E negative 9. So that's 350 nanometers. So this is in units of meters. And we're going to now define our step size, delta x, or we're going to just call it lowercase dx. It's equal to lambda min divided by 20, like I showed before. And we're going to set our step size to be dx divided by the speed of light, like I showed before. Okay, so now let's start the actual time iterations now. So we're going to make our for loop for n in range n max. So that is just this for loop right here, right? And so what do we need to do? Well, we need to update magnetic field boundaries, right? And that is just this formula right here. So this is hz at Jmax minus 1, right? Because we're in Python, there is no Jmax element. It ends at Jmax minus 1, so that's why I'm saying that. And that's going to be equal to hz, the previous time step, right? at j max minus 2. So that is just this formula right here, and n minus 1, so it's the previous time step. Okay, then we're going to for loop through the spatial components of our simulation domain. So for j in range j max, and we're going to say hz at j is equal to hz previous, so the previous time step at j, plus, right? Yeah, sorry, plus dt divided by dx times mu 0 times ex, is it j plus 1 or just j? It's j plus 1 minus ex at j. All right, so ex at j plus 1 subtracted by ex at j. Okay, I'm going to ignore the source right now, but I'm going to put a note in here. Magnetic field source. Okay, next we're going to do the electric field, so I'm just going to copy and paste this code here. And I'm also going to make a note here. Update magnetic field. There we go. It's always good to put comments in your code. So this is not that bad. So we're going to now make this the electric field boundary, and the electric field. So first ex at 0 is equal to ex at the previous time step at 1. Perfect. And then we're going to update update electric field. There we go. And similarly, so this is just ex at j, ex previous, epsilon. We didn't define epsilon yet, so epsilon can actually be an array of primitivities, but for now we're just going to set it equal to epsilon 0. We can actually add in some materials later on. And now for the curl, we need hz. This time it's not j plus 1, it's just at j, minus hz at j minus 1. We also need to look at our for loop ranges here, right? So for the magnetic field, it goes from 0 to j max minus 1. Okay? And for the electric field, it goes from 1 to j max. So magnetic field is from j2 up to j max minus 1, and here it's just 1 to j max. Okay, and finally I want to also add in an electric field source. Okay, let's do that. First of all, let's just make sure that this thing runs without any issues. There we go, we just ran a simulation. Look at that. And there was no errors, which is a new thing for me. Okay, so let's define a source function. So we're going to find that just right here. And we're going to read in a time t. And here, I'm just going to say that ex at j source, we haven't defined j source yet, but okay. We're going to say plus equals source function, and I'm going to give it time step n, right? No, I need to give it time step n plus 1. So let's do that. Time step n plus 1. Okay. And source function is going to return a modulated Gaussian. So np.exponential of negative t minus t0 to the power of 2 divided by tau to the power of 2. We need to define t0 and tau. Multiplied by numpy.sine times w0 times t, where w0 is the frequency, is the center frequency of your Gaussian pulse. So t is going to be an integer. It's going to be the time step. So we need to define t0, so the delay, and tau in terms of time steps. So we're picking n max to be 2,000 time steps. So let's pick tau. Let's pick our width to be, let's say, 300 time steps. And then I usually define my delay, so the t0, in terms of tau. So I'm going to say that t0 is equal to tau times 3. That will provide plenty of delay. And finally, we need to define our angular frequency of our pulse. So let's define lambda 0. So let's define the center wavelength of our pulse, which is, in my opinion, a lot easier. So we're going to put it in the middle of the visible spectrum, so 550 nanometers. And then omega 0, or W0, I should call it, is just equal to 2 times numpy dot pi times the speed of light divided by lambda sub 0. Now, p is an integer here, but omega 0 is has the units of radians per second. So we need to actually make sure that our time unit here has the units of seconds. So I'm just going to multiply by the time step size, delta t. Okay. And we need to define J source. So we'll put that up here. J source. Let's put it at the 100th base step for now. Okay. Did I do everything correct? I have a code off screen that I'm not going to show you guys, but this code actually does work, and I believe I did everything correctly. So the last thing I'm going to do, so obviously I haven't done the magnetic field source yet, and there's a reason for that. I just want to show you what happens if you don't put it in the magnetic field source. I'm now going to plot the electric field. Now, I don't want it to plot at every time step because plots are very computationally expensive. We're going to plot it every 10 time steps. So if t modulus 10, sorry, not t, sorry, if n modulus 10 is equal to 0, then we're going to do our plot. So this just says if m modulus 10 is only equal to 0 when m is a factor of 10. So this will be at the 0th time step, the 10th time step, the 20th, 30th, 40th, etc., etc., etc. So we're going to plt.plot EX, which is the electric field for now. Plt dot, and we're going to make the y limits constant, so between -1 and 1, and plt dot show, and plt dot close. So if we run this, what's wrong? Oh, it's n, not m. N. There we go. So now if we run this, let's see what happens. Oh, did I just Control Z? My bad. Save. There we go. Alright, now let's run this. Whoa, what happened? We have, so that's what an instability looks like. Let's find out why we have an instability. Dx is set to be 17.5 nanometers. dt equal to that. All right. This is interesting. I'm going to stop recording for a second, and I'll get right back to it. Okay, after cutting out for a couple seconds there, I'm back, and I found out what the issue was. So if you remember, this was, well, I mean, of course you remember, this was only a second for you, but yeah, we have this sort of instability happening, and the reason for that was I forgot something very simple here. I need to update hz previous. So here we can just say hz previous is equal to hz at j. So what do we do here? We're updating hz at the current time step using the previous time step. But now that we're done that, all we have to do is now say, well, hz at previous is now equal to hz at j. Okay? And we need to do the exact same thing for the electric field, so let's do that. Ex previous at j is equal just to Ex at j. And we also need to do the same thing after the source, right? So Ex previous at j source, here we go, is equal to Ex at j source. You're actually updating EX and J source twice, once inside this loop and once outside, but that's okay. Now that we have those, we should see that our instability completely disappears. So let's watch what happens here. So you can see something happening here at around 100, which is where we're introducing our source. And here is our modulated Gaussian. Look at that. It's beautiful. And it's going to go off, and it's here you can see it's hitting the boundary and it's going off to infinity. And if you're not convinced of that, I'm just going to make the Gaussian a bit shorter and rerun this simulation here. So I'm also going to restart the console. All right, so I'm going to make tau equal to 30. So it's a much smaller pulse. And I'm going to make J source in the middle of our simulation domain, so 250. And that way you can see the source going off in both directions. Okay, so watch this. So you can see it, look at that. And it goes off and it's going to hit the boundaries and go off to infinity. So the source does not bounce back in. All right, so let's, actually what I'm going to do is I'm going to get rid of the boundary condition so you can see what happens without the boundary condition. So watch. We start the source in the middle here, it goes off and it's going to hit the boundaries and it reflects right back in. We don't want that, right? So that's why we need those mirror boundaries. It's cool, you get to watch the interference itself, hits the boundary again, reflects back in. So that's what I meant when I said if you don't do the boundary conditions, if you just let the boundaries be equal to 0, you're defining the boundary to be a perfect electrical conductor, which means that it's acting like a mirror, so it's just bouncing the fields back inside again. So let's not do that. Let's keep those boundary conditions there. And also you saw that when we introduced the source, just the source for the electric field, again the magnetic field source is not there yet, we have waves propagating in both directions, which is fun. It's fine for some applications, but you might want to see unidirectional propagation. You want the wave to travel in one direction. So let's fix this, shall we? So we're going to add in our magnetic field source. So HZ at, remember this is J source minus 1, right? J source minus 1. Okay. Let's go back to spider. There it is. Source minus 1 minus equals and just add n. So if we do that, and again we need to update the previous field, right? So this is at J source minus 1 equal to this. We run this. Whoa. Okay. So something's not. Oh, right. I didn't divide by the impedance, right? You got to divide by the impedance. That's why. All right. Now, here we go. Look at that. The source only travels now in one direction, and it goes off to infinity. All right. So let's make sure. Put J source a bit closer to the beginning of the simulation. So let's make J source equal to 10. And here you go. You have a wave starting over here, and it just travels across the domain. It has an amplitude of 1. And it's going to go off to infinity like that. All right, so now we've actually simulated light in vacuum. So we're introducing a pulse in vacuum, and we're just watching it travel. So let's make something a bit more interesting. Let's add in a dielectric slab. So now instead of epsilon equal to epsilon naught, we're going to make this into an array of ones of size J max. We're going to multiply this by epsilon naught. Okay, so that's the same thing we had before, only now it's an array. And over here, we have to acknowledge that it's an array. And now if we want to add in a thin film, let's say epsilon at, let's go from 200 to 300. So it's going to be 100 cell thick dielectric film. And we're going to set this to be a dielectric constant of, say, 10, right? And we're going to multiply that by epsilon naught, of course. So now what we have is a thin film in the middle of our simulation domain, and it has a thickness of 100 cells, which multiply that by the step size. Okay, well, it's not that thin. It's a 1.75 micron film. Maybe we should make that smaller. Let's make that smaller. Let's do from 250 to 300. Okay, so now it's going to be closer to, I can't do mental math, 850 nanometers. Yeah, okay. And we're going to add this to our plot. So let me just show you what I mean. I'm going to make a material profile array, material profile, and that's going to be equal to epsilon greater than epsilon naught. So basically this is just going to be an array of ones wherever there is material, and an array of zeros in vacuum. If you do not believe me, yeah, I'm going to F9 this, and I'm going to just plt.plot material prof, and here you can see it's zeros, and then here's our thin film of 1 here. And the reason why I defined that is because I'm going to make our plot here a bit more interesting. Plot material prof. So now we can see where the material is relative to the actual electric field. Okay, great. So now let's run this. Let's see what happens when the light hits a thin film. Oh, okay, I see an issue here. Anyway, here you can see it's hitting there, and you can see some total internal reflection happening inside of our thin film. And you can see the light's not total internal reflection, sorry, just reflection, sorry. And it's just bouncing back and forth inside that film there and letting out a bit of light each time. So that's really neat. So this is what it looks like when you have light hitting a thin film material. Okay, so I'm going to Control C that. Okay. This code is relatively slow, and that's because we are using a bunch of for loops. For loops in Python are slow. So what I am going to do is I'm going to vectorize everything here. And the way I do that is I'm going to replace these for loops with vector expressions. So let's get rid of this for loop here. I have to remember it's from 0 to j max minus 1, right? So instead of a for loop, all I have to do is put in hz from 0 to j max minus 1. And similarly here to j max minus 1, and here to j max minus 1. And this guy here is going to be from 1 to j max. And then this guy here, we can just get rid of the indices. So that's what's called vectorizing. So we've placed the for loops, and we're just doing vector math on all these guys. All right, so let's see. I want to make sure that this actually works. Yeah, all right, perfect. So yeah, it's going to be it's the exact same simulation. It's just great. The magnetic field calculation is now a lot faster. So let's do that now for the electric field. So this one here is going to be okay. So before I get rid of the for loop, let's go from 1 to 1 to n. So you don't need to put anything there. It's the beauty of Python. Again, 1 to end. 1 to end, 1 to end, and this one here is minus 1, so it's going to be 0 to j max minus 1. If you're not familiar with vectorizing, I highly recommend it, especially in Python if you're using NumPy, because these formulas here, like if you do a for loop in Python, it's literally repeating that calculation over and over again. Whereas if you vectorize it, the code that's actually running this is in C, so it's a lot faster. It's like pre-compiled code. Okay, so now let's run this again, and it's, well, you can't really tell it's faster because of the video, but you have to believe me that this is way faster. The video, the plots slow down the program a lot, so the plots are kind of a bottleneck here. Okay, so yeah, we've seen enough of that. So if I just comment out the plot, and if I run it, it's done. Look at that. Ready? Run. Over. Whereas with the loops, I'm not going to rewrite the loops. With the loops, though, it takes a few seconds for the simulation to run. This one here, vectorized, is sub-second. You know, I love it. Okay, sorry guys, I'm a bit of a weirdo. For now, I think that's I'm gonna end this video. Thank you guys so much for watching. I hope you found this useful. Be sure to comment any questions you have. I'll try to answer them as much as I can, though if you ask the question in a few months, I probably won't answer it. So if you need to answer it, you need to ask within the first few days of me posting this video for me to answer them. Thank you so much, guys.